Hi everyone, welcome to another one of our research videos. We give a brief summary of scientific research that we've undertaken. I'm Raphael Swickerman, co-founder of Vedantia Research. Today I'm going to talk about modelling the effectiveness of silvopastoral trees in terms of reducing sediment delivery to streams. If you watched the first video I did featuring my PhD research, you would have seen me talk about quantifying the effectiveness of trees and reducing erosion. In this talk I'm going to extend that to focus on landslide derived sediment delivery to streams. Water quality focus here. How can we determine where to target tree planting based on coupling landslide susceptibility models? They inform on where we can expect landsliding to occur in future, and sediment connectivity models. They inform on the likelihood then of the landslide delivering sediment to streams. Ultimately, I want to demonstrate how targeted planting can significantly increase the cost effectiveness of erosion and sediment control. Now, like I said, the research I'm presenting in this video builds on the studies I presented in the previous video. If you haven't seen it, I'd recommend going back to view that first. But I'll just recap very briefly here on this slide. So what you're seeing is an example of the landslide susceptibility model, showing the difference between a treeless, pasture-only baseline in the top left, so the tree effect has been removed from the prediction, and then incorporating the actual tree cover in the prediction below. So the red areas are highly susceptible to landsliding. This is where we would expect future landslides to occur predominantly, and the difference between these maps shows the effect that the trees are having in stabilising slopes. So you can see the eucalypt grove, the aerial photo showing the actual tree cover that's incorporated here and has been removed from this view here. Okay, now this is purely a focus on shallow landsliding, and in contrast I'm going to discuss how this picture might change when we focus on sediment from these landslides. How does the perspective on tree performance and targeting for both erosion and sediment control change things? So those are the research questions being asked of this presentation. Okay, so if retaining soil on slopes isn't the only priority, but also sediment and water quality outcomes, then we first need to link the hill slopes to the streams. And you can see in this photo that some landslides clearly deliver sediment to the adjacent stream channels and others less so. And so I developed a statistical landslide connectivity model using a set of 2,000 landslide scars and 1,200 debris tails mapped in this image following the 1977 storm event in the Wairarapa. And the model is aimed at informing on the likelihood of delivering sediment to streams. Now just briefly, the model is based on a binary distribution of connected and unconnected landslides, whereby connectivity is given by the spatial intersection of debris tails and streams. So a landslide triggered on a slope, delivering sediment to streams, and that is defined by the intersection of the mapped debris tail intersecting a buffered stream channel. And if the intersection is not given, then it's considered to be unconnected. Now, similar to the landslide susceptibility model, a machine learning algorithm trains a model based on a set of morphometric variables such as distance to stream or slope gradient. Then subsequently the model can also be used to investigate the factors that determine connectivity. Now here's an example of a prediction of sediment delivery by shallow landslides to streams. High values close to 1, so in the areas of red, indicate that if landslides are triggered here, they're likely to deliver sediment to the channel. Now these predictions can then be classified into 3 classes, low, medium and high, based on the thresholds derived from the probability distribution of this black curve. And you can see, for example, here 80% of connected scars have probability values greater than 0.46, and so that defines the threshold for this first class high and so forth. Now, it basically follows the same procedure as the classification of the landslide susceptibility probabilities that I showed in the first video. So the coupling of landslide susceptibility and connectivity is achieved through the intersection of these three classes in each domain, the landslide susceptibility and the connectivity classes, and that results in 9 classes. And you can see it in the map. So we have in the legend here the dark green areas, they symbolize the low susceptibility and low connectivity class, all the way through to the red, which represents the highly susceptible and highly connected areas, shown in the red here on the farm. And here we're contrasting a treeless pasture baseline with the actual tree cover, and you can see where the existing trees are located by the symbols here. The round dots represent a eucalypt. We've got poplars and willows with the crosses, some carnica here with the plus symbols, and the conifers, not many in this picture, but they were squared. So interestingly, the consideration of connectivity has approximately halved the area that requires treatment if sediment mitigation is the focus compared to soil erosion alone. And to demonstrate this, I can show a simplified example using 3 classes showing the potential for sediment delivery in the next slide. And right now what I'm showing you is the landslide susceptibility maps that you already know. And if you watch closely, when I go to the next slide, you can see a similar story is told as with the susceptibility maps, but some of those steep upper slopes are no longer red, and that means they're unlikely to be a sediment source, because landslides triggered on these steep upper slopes are more likely to deposit their sediment on the slopes rather than delivering sediment to the stream channels. Now here just a farm-wide view, similar story. Here the treeless scenario of potential sediment, and then the actual tree cover incorporated in the prediction. And you can see that the trees have made a really significant difference to this farm. Only a small fraction of the entire farm is a potential sediment source from landsliding. And you can see the remaining red areas could be areas that are then targeted with future tree planting. Okay, and finally, these models can also be used to consider a range of scenarios. Now, as an example, we here contrast the effect of targeting the high zone, which is shown here in the black, and then covering the entire farm in a 15 by 15 metre grid, shown in those with the points. And this enables us to determine what the maximum reduction in landsliding and sediment delivery is, and the cost effectiveness of a targeted versus a non-targeted mitigation. Obviously, less trees will be required to plant out only that one class of highly susceptible and highly connected slopes versus planting the entire farm. And we can then work out what the average cost would be on a per hectare basis of a targeted versus non-targeted approach. So in terms of scenario modelling, there are ultimately 4 scenarios that we consider. These are showing the predictions for those 4 scenarios, starting with the top left is that treeless pasture-only baseline. That's always the baseline that we compare to when calculating reductions achieved. Then the actual tree cover shown in window B, the targeted mitigation scenario where we target that high class, and then blanket planting shown in window E with those green crosses, in contrast to just those red areas in the high class. Okay, so these scenarios were computed for 50 farms in the Wairarapa, each of these farms larger than 300 hectares in size, total area of almost 37,000 hectares. And this is now the aggregated view of the 50 farms for the first two scenarios. So we see a treeless scenario on the top left, and in this scenario 6.5% of the farm area, so that's 2,400 hectares of a total of 37,000 hectares, would be both highly susceptible to shallow landsliding and also have high potential for sediment delivery to the stream network. Now if we look at the graph on the right, it includes the existing trees. That class has now been reduced to less than 5%. Now the change in the distribution across these 9 classes amounts to an estimated reduction in sediment delivery of 24% across the 50 farms. Now the 2 graphs below show the aggregated results for the targeted mitigation planting and planting across the entire farm. And the targeted mitigation of highly susceptible and connected land has potential to reduce sediment delivery by 34%, shown in this table, compared with the pasture baseline scenario, and the maximum reduction in sediment delivery using that 15 metre spacing is 56%. Now this graph shows the same result as the table I just showed with the summary table, but we now see the variation across the 50 farms, and there is some variation indeed, and that's because there's, for example, with the actual vegetation, there's just a differing amount of vegetation across the 50 farms. That has an impact obviously, and also the variation in the topography, the lithology, etc. all has an impact on the reduction achievable. Now it's this second graph here that I would just like to spend a little more time explaining. Now I mentioned only 6.5% of the land area of those 50 farms is both highly susceptible to shallow landsliding and has high potential for sediment delivery to the stream network. Targeting this area would result in a reduction in sediment delivery of 24% across the 50 farms at a much lower cost compared to a non-targeted or random approach to tree planting. In fact, I calculated a 10-fold increase in cost effectiveness of measures based on costings for pole planting given to me by Greater Wellington Regional Council. And here's a concrete example of what this means. I've broken the costs down, you can see on the x-axis, the dollar value per 1% reduction in sediment delivery on a per hectare basis. Now, for example, a farm of 1,000 hectares, the average cost to achieve a 1% reduction in landslide-derived sediment is $2,900 for a targeted mitigation and $26,200 for non-targeted. So that's multiplying by 1,000 hectares to achieve a 1% reduction. Now you can multiply that by 33% to see what the maximum reduction achievable is. We know it's the maximum on average is 33%, and so multiplying that cost by 33 to get a 33% reduction would amount to a $96,000 cost for a targeted approach and an $865,000 to achieve the same result of 33% reduction in sediment delivery but using a non-targeted approach. So targeted sediment control is 10 times more effective than a non-targeted approach. Okay, and that brings me now to the summary. Got a few points here. So the right tree in the right place can be very effective at achieving outcomes. I think that's what this demonstrates. And mitigation can be targeted to sediment source locations by coupling landslide susceptibility, answering where can we expect landslides to occur and where can we expect connectivity to be greatest. And then we've also, I've just shown you, demonstrated that targeting mitigation to areas that most need it, highly susceptible, highly connected areas, increases the cost effectiveness of those measures. In fact, it's a 10 times cost effective compared to just a random non-targeted approach. So very important from a financial point of view. And that's what we're worried about here at Vedantia Research. We're really aiming to optimise farm landscapes to achieve more profitable farms with cost-effective measures. So what I've presented here today and in the previous video, it's all been published, peer-reviewed, and I'll provide links to these publications below if you're interested to delve into some of the details. I've only really been able to touch the surface of these studies, so provide some key outputs there, but if you're interested in more detail, please go ahead. And we're always really interested in any thoughts and any comments you might have. Leave a comment below the video. The best way to get in touch with us is just to use our contact form on our website, and we'll get back to you. Now, if you've enjoyed this video and found it interesting, don't forget to hit the subscribe button to receive similar content in future.